Hello everyone, this is Surajit and you are welcome to our channel. In first few lectures we have talked about different kind of coordinate system, and then we also talk about different mathematical tools like curl, gradient, divergence, and one special function, direct delta function. So now we'll start electrostatic part. So today we'll talk about Coulomb's law, and then using Coulomb's law, we'll see if we have a more than 2 charges in our system, let's say 3 charge, 4 charge, or 5 charge, then how we can calculate electric force on a particular charge uh, based on the superposition principle. And then we will also learn how to write electric field due to a point charge. And then again, like if we have a single point charge, we can write the electric field using Coulomb's law. But if we have more than single point charge, let's say 2 charge or 3 charge or 5 charges, 5 point charges, and if we want to find out electric field any arbitrary point, then again we have to use a superposition principle. So we'll discuss superposition concept of superposition principle of electric field, and then we'll see instead of discrete point charge, if we have a continuous charge, then how we can write the electric field. So we'll use the concept of elementary length, elementary volume, and elementary area with superposition principle to find out the electric field due to continuous charge distribution. Yeah. So let's start with Coulomb's law. So right here Coulomb's law. In 1785, one famous French experimental physicist, Charles Augustin de Coulomb, Charles Augustin de Coulomb actually gave this law, and that's why this law is called a Coulomb's law. And he found this law actually accidentally. Actually, during the, I think around 1780, there was a competition in Paris, and competition is about who can make a frictionless compass. So Coulomb was doing this experiment, and accidentally he found that two charges carrying object repulse each other, or two charges carrying object apply force on each other. And later, to measure this force, Coulomb has developed a machine which is known as Coulomb's torsion balance machine. So from this experiment, he written a few statements, and which is together known as Coulomb's law. So what was this statement? His first statement was the force between two charges is directly proportional to the product of the magnitude of their charges. Second statement was you also found that this force is also inversely proportional to the square of the distance between them. And third observation was the direction of force is along the line joining the position of charges. And same type of charge charges repel each other and opposite kind of charge attract each other. Attracts each other. So it's all three statements together known as the Coulomb's law. Coulomb's law. So now if we want to write this statement in terms of mathematics, how we can write this? So for that, let me just draw a figure first. Let's say this is a coordinate system. This is x-axis, this is y-axis, and this is z-axis. And we have two charges. One charge is q1 at a distance r1 from the origin, and another charge is q2 at a distance r2 from the origin, and the distance between them can be written as r21 is equals to r2 vector minus r1 vector, and this is q1 charge and this is q2 charge. Okay, so now if we want to write this statement in terms of mathematics, how we can write? So according to first statement, the force between these two charges q1 q2 is proportional to the product of these two charges q1 q2 when r21, that is the distance between these two charges, is fixed. Distance between those two charges is fixed. And then according to second statement, this force is also inversely proportional to the square of the distance between these two charges. So in this case, distance is mod of r21 when product of these two charges, that is q1 q2, is fixed. q1 q2 is fixed. So if we want to write the net force in terms of magnitude, so the repulsive force or the force between these two charges can be written as some constant, which is known as Coulomb constant, into q1 q2 divided by the distance between these two charges square. Things. And in this Coulomb's law, usually we replace by a constant. This is Coulomb constant is replaced by this 1 by 4 pi epsilon naught q1 q2 divided by r21 square, where the value of this Coulomb constant 1 by 4 pi epsilon naught is almost 9 into 10 to the power 9 SI unit, and this epsilon naught is called permittivity of free space. The permittivity of free space, and this value of epsilon naught is written 8.85 into 10 to the power minus 12 in SI unit. SI unit. Okay, so this is the force, and then if we combine the third statement is related to the direction of the force. That means this force is actually a vector quantity. So in that case, if we want to write force on q1 and q2, and let's say both are same type of charge, so for that let me again draw another figure. So in this figure, first figure, we have x-axis, y-axis and z-axis, and we have two charges q1 and q2, and they are same kind of charge. Either they both are positive or they both are negative. So in this case, we are considering both are positive. q1 and q2 both are positive, and position vector of q1 with respect to this origin is r1 and q2 is r2. Position vector of q2 is r2. So the distance between them can be written as r21. R21 mean r2 minus r1 vector. Okay. Similarly, let's say we have another figure, x-axis, y-axis and z-axis, and we have two charges q1 and q2, but now they are opposite kind of charge. Let's say q1 is negative, minus q1, and q2 is positive, plus q2, and again their position vector is let's say r1 and r2 respectively. So in this case, if this is the r2 vector, now we can define r2 vector r2 minus r1 vector. Yeah. So now according to the first statement, what is written here, that the force is along the line joining the two position of two charges. So force will be always, if we connect these two line like this charge and this charge, so we have connect these two charge by the straight line, so force will be along the straight line. Now it will be repulsive or attractive, that will be depends on the type of the charge. So first case, in this case q1 q2 both are same charges, same type of charges, so in this case force will be repulsive. So that's mean if we want to find out the direction of force on q1 because of q2 because of q1, so since they will repulse each other and along the line, so in this case the force on q2 will be in this direction. Force on q2 will be in this direction, and force on q1 because of q2, again it will be also repulsive, so it will be along this direction. It will be along this direction. So how we write force on q2 because of q1? We represent it in this way: force on q2, so f2 because of charge q1. Charge q1. And how we'll write this force on q1 because of q2? Then we'll write in this way: force on q1 because of q2, so f12. So f12 is the force on q1 because of q2, and f21 is the force on q2 because of q1. So in this case also, if I want to write the directions of force on q2, so in this case, since they are opposite kind of charge, so direction force will be attractive in nature. So in this case, if we want to find out the directions of electric force on q2 because of q1, since they will attract each other and force will apply on them along the line, so in this case force on q2 because of q1 will be in this direction. So f21 will be in this direction. And again, if we want to write the force on q1 because of q2, since the force will be always attractive in this case, so in this case directions of f12 will be along towards right. So this will be the direction of force. This will be the direction of force. So now if I want to write this f12 for both the cases vector form, then how we can write? So just write here the force acting on charge q, acting on charge q2 due to q1 is given by I will represent it force on q2, so we'll write f2 and then 1. So f21 is equals to 1 by 4 pi epsilon naught, and then product of these two charges q1 q2 divided by r21 square. This is the magnitude, and then directions will be in this direction. So this will be the directions of actually r21 vector, so we can write r21 cap. R21 cap. Now if we want to, if we multiply with r21 in denominator and numerator, so what we can write? We can write 1 by 4 pi epsilon naught q1 q2. So when we will multiply r21, magnitude of r21 with this unit vector r21 cap, that will actually give us r21 vector, r21 divided by r2 cube, magnitude of 3 cube. Okay, so this will be the force, mathematical expression of force that's acting on Q2 because of Q1, because of Q1. Similar way, we can also write the force on Q1 because of Q2. So in this case, we'll write force F1, 2. That is force on Q1 because of Q2. And this can be written as 1 by 4 pi epsilon naught Q1 Q2. So now this directions of force will change. So what we can write here, we can write simply R12 cube into R12 vector. Okay, R12 vector. So the magnitude of F12 and 21, because magnitude of R12 and R21 will be same. So that's mean the magnitude of F12 and F21 will also be same, but the directions of R12, R21 will be along this direction and R12 will be along this direction. So we can write F12 is equals to minus of F21. F21. And for this case, second case, if I want to write the force on Q2 because of Q1, how we can write this? So in this case, simple, if you consider that both are same kind of charge, then what will be the force on Q2? It will be 1 by 4 pi epsilon naught Q1 Q2 divided by R21 cube and then R21 vector. But now this charge is one charge, they are opposite kind of charge, so force will be actually attractive. So what we can do, we can just simply multiply the negative sign here. That will give you, for the second case, that will give you the force on Q1 because of force on Q2 because of Q1. And same way, if you want to write force on Q1 because of Q2, so what we can write 1 by 4 pi epsilon naught Q1 Q2 divided by R12 cube into R12 vector. And again, in this case, we have to multiply with a negative sign. Okay. So this way we can write a force between these two charges. When you write in this form, you are actually writing in vector form, so you'll get magnitude as well as direction. Okay, so now we learn how to write or how to calculate the force between two charges. But in our system, if we get more than two charges, then how we can write the force on a particular charge? So let me draw a figure first. Let's say this is again a coordinate system, x-axis, y-axis, and z-axis. And now in our system we have, say, n number of charges. This is Q1, this is Q2, this is Q3, and ordered up to, say, let's say we have n number of charges. So Qn, this is Qn. Qn. So now if we want to calculate a net force on this Q1 because of other charges, how we can calculate that force? So what we have learned from the Coulomb's law, if we have two charges, then we can calculate the force on this one charge because of other charge. But if we have in our system, if we have more than two charges, then we cannot directly use Coulomb's law. For that, what we have to do, we have to use actually superposition principle. What we have to use? Superposition principle of force. superposition principle of force. Yep. So what is this principle? So according to this principle, what we have to do? First, we have to calculate force on Q1 because of only Q2, only Q3, up to dot only Q1. So what is the idea of this superposition principle is that, let's say this is our charge distribution, but it is assumed in this way that there are only Q2 charge and Q1 charge at a times. There have a Q2 charge and Q1 charge. If there is only Q1 and Q2 charge, then what will be the force on Q1 because of Q2? That we can write. We have two charges, we can write what will be the electric field. And then next step we'll consider there are only Q3 and Q1 charge, and then what will be the force on Q1, that also we can write. And similarly up to n, so once in we can consider that there are only Qn charge and Q1 charge. So at that time what will be the force on Q? So that's mean what we are trying to do here, we are actually calculating the force on Q1 because of individual charges Q2, Q3, Q1 and Qn. And then since all these charges are simultaneously present here, so according to this superposition principle, the net force on Q1 will be actually summation over all the vector quantity, all the individual force. Individual force. So let me just write here one line and then we can write what is the statement this principle says us. Let's say first write the force on Q1 due to Q2 only is F12 is equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R12 cube into R12 vector. So once you know the position vector of Q and once you know the position vector of Q2, then you can calculate this vector. So this will be the R1 vector, R12 vector, and directions will be along this direction. Okay. And then same way you can also write the force on Q1 due to Q3 only is F13 is equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R13 cube, then R13 vector. R13 vector. So this will give you the force on Q1 because of only Q3. Same way you can also write the force on Q1 because of Qn. The force on Q1 due to Qn only is F1n is equals to 1 by 4 pi epsilon naught Q1 Qn divided by R1n cube. into R1n vector. Okay. So in this way, we can write a force on Q1 because of individual charge Q1, Q2, Q3, Q4 up to Qn. And then since all these charges present here simultaneously, Q1, Q2, Q3 and up to Qn, so according to this superposition principle, according to superposition principle, the net force on Q1 is F net is equals to the vector sum of all forces. Vector sum of all forces, because all the charges are present there simultaneously. So what we have to do, we have to add all these force together. So F12, F13, F14 to F1n. So if we added them together, then we'll get the net force on Q1. Okay. So this is the concept of superposition principle. So when will use superposition principle of electric force? When there are more than two charges. If I have a two charge, then we can directly use Coulomb's law. But if we have a more than two charge, then what we have to do? First, we have to calculate the force between two charges using Coulomb's law, and then we have to add all these forces together. From there, we will get the net force on a particular charge. Okay. So let's solve one example related to the superposition principle. So see here what is written here. What is written here, that three identical point charges of magnitude Q are placed at respectively 1, 1, 2, 2, 3, 3. Find out the net force acts on the charge which is placed at 3, 3, 3. Okay. So let me draw just a schematically diagram here. So let's say this is on 1 point, this is 2, 2 point, and this is 3, 3 point. 1, 1, 1, 2, 2, 2, and this is 3, 3, 3. Okay. So I have three different points, and at this point we have placed three identical charges. And let's write it this way: Q1, Q2, and Q3. So all Q1, Q2, Q3 have same value. Mod of Q1, mod of Q2, and mod of Q3 is equals to Q. Okay. So now what has been asked in this question? So what will be the net force on Q1 because of other charges? So now the question says how many charges we have in this system? 3. Q1, Q2, Q3. So it is more than 2. So if we want to calculate force on Q1, what we have to do? We have to use superposition principle. So for that, what we have to do first? First, we have to calculate force on Q1 because of individual charge, that is because of only Q2 and because of only Q3. And then we'll add these two forces together. That will give us the net force on Q1. So calculate first individual force. So right here, the force acting on charge Q1 due to q2 is f12 is equals to 1 by 4 pi epsilon naught q1 q2 divided by r12 cube into r12 vector, not 2 1 1 2, r12 vector. Okay, so we know the value of q1 q2 both are q, so what we have to calculate only r12 vector. What is r12 vector here? r12 means r1 minus r2, that is position vector of q1 with respect to q2. This vector, this is r12. So how we can write r12 vector? So we know the coordinate of both charts q1 and q2, so we can write r12 vector in this way. So we have to write position vector of q1 with respect to q2. So for that, what we can do, we have to write x coordinate of q1, that is 3, minus x coordinate of q2, 2 into I cap, and then for same way y coordinate of q1 minus y coordinate of q2 into j cap, plus z coordinate of q1 minus z coordinate of q2 into k cap. So after simplifying this, what we'll get? We'll get I cap, j cap, k cap. Okay, this is the value of r1. And now if we want to write the magnitude of r12, so what we'll get? We'll get root 3. Root 3. So now we know the magnitude of r12, and we also know the value of r12. So we have to put it here, calculate the value of f12. So f12 will be 1 by 4 pi epsilon naught. And then q1, q2 both are q, so q square divided by cube of r12. So it will be 3 into root 3. And then r12 vector is I cap plus j cap plus k cap. K plus j cap plus k cap. So this is the force on q1 because of only q2. Because of only q2. Same way we can also write the force on the force acting on charge q1 due to q3 is f13 is equals to 1 by 4 pi epsilon naught q1 q3 divided by r13 cube into r13 vector. So in this case, what is r13 vector? So this is again the position vector of q1 with respect to q3. This is vector. This is r13 vector. Okay, r13 vector. So from figure, what we can write, how we can write the value of r13? So we can write r13 vector is equals to again the position vector x coordinate of q1 minus x coordinate of q3. So in that case, x will be 3 minus 1 I cap, and for y coordinate also it will be 3 minus 1 j cap plus 3 minus 1 k cap. 3 minus 1 k cap. So from here, what we can write r13 vector. So if we simplify this thing, what we'll get? We'll get 2 into I cap plus j cap plus k cap. This is the r13 vector. And what will be the magnitude of r13 vector? So it will be 2 into root 3. 2 into root 3. So once you know the value of r13, you know the value of q1, q3, both are actually q. So therefore, what will be the value of q13? Let me write in the next page. So what will be the value of q13? Force on q1 because of q3 will be 1 by 4 pi epsilon naught, and then product of q1 q3 is q square divided by cube of r13. So what will be the cube of r13? Will be 8 into 3, so 24 3 24 root 3, and then r13 vector I cap plus j cap plus k cap. So if we simplify more it, what we'll get? We'll get 1 by 4 pi epsilon naught q square divided by 12 root 3 I cap plus j cap plus k cap. Okay. So now we know the force on q1 because of individual charges q2 and q3. Now according to superposition principle, so if we want to calculate the net electric field on q1, we have to use superposition principle. And according to superposition principle, what we can write? According to superposition principle, the net force on q1 is F net is equals to sum of these two forces, 1 2 vector sum of these two forces, F12 and F13. F12 and F13. So we have already calculated here F12 and F13. So just put them together. So what we'll get? We'll get 1 by 4 pi epsilon naught q square divided by 3 into root 3 I cap plus j cap plus k cap plus 1 by 4 pi epsilon naught q square divided by 12 root 3 I cap plus j cap plus k cap. So if we simplify there, what we can take 1 by 4 pi epsilon naught common, q square by 3 root 3 we can also take common. Then what we'll get? We'll get q square divided by 4 pi epsilon naught 3 root 3. And then what we'll get here? 1 by 4. So we'll get I cap plus j cap plus k cap plus 1 by 4 I cap plus j cap plus k cap. So this will give you actually 5 q square divided by 4 pi epsilon naught into 12 root 3 I cap plus j cap plus k cap. I cap plus j cap plus k cap. So if we have this type of charge, like more than 2 charges in our system, and if we want to calculate the net force on a particular charge, then what we have to do, we have to use superposition principle. And here we have solved one problem where we have noticed how to use this superposition principle. Okay, so now we know how to calculate net electric force on a particular charge when in our system we have more than 2 charges. So next, what we learned here, what will be the, what is electric field? What is electric field? Before that, let me just write one thing here. What is the unit of force? This is Newton. Newton. Okay. So now write here electric field. Field. For that again, let me just let's say we have 2 charge plus q charge and another at a distance r from this charge, plus q charge plus q charge, and this is the directions of r cap. So this is also plus q charge. So now if I ask you what will be the force on small q because of capital Q, what will write? So right here, the force on small q due to capital Q is F is equals to 1 by 4 pi epsilon naught capital Q small q divided by square into r cap, r square into r cap. And now if I divided this force by small q, then what will get? F divided by q is equals to 1 by 4 pi epsilon naught capital Q divided by square into F. So here this equations give the force on Q1 because of capital Q. But once you divided this force by small q, then we can write the force per unit charge because of capital Q at a distance r. So that force per unit charge because of capital Q at a distance r, that means at this point it's called electric field. Electric field. And how we define it? We symbolize it by E. So in this case, E will be the electric field of the capital Q charge at a distance r. And how we can write this electric field? So it will be 1 by 4 pi epsilon naught capital Q divided by r square into r cap. Okay. So if you have a single point charge and if we want to calculate electric field at any point P, then what we have to do? First, we have to find out the distance of the point from the position of the charge. And so once you know that position, if we represent that position, this distance by r, then we can write this electric field at that point will be 1 by 4 pi epsilon q divided by r square. That will be the magnitude, and r cap will give you the directions of electric field. Okay. So now in this case, if the source charge is positive, then charge on the plus q will be always repulsive, so it will be always away from the source charge. But if source charge is negative, then electric field, directions of electric field will be always towards the source charge, because let's say if you have a minus q charge, and if we place a unit charge at a distance r, then what will be the force? Force will be q divided by 4 pi epsilon naught r square. But in this case, this charge is negative, so force will be attractive. So in this case, force will be in this direction. That's mean electric field at this point will be towards the source charge. Towards the source charge. Okay. So let me just write this point, because this concept we have to use and we're going to solve the numerical problem. So if we have a positive charge and if you have a negative charge, and how this electric field will change actually. So if you have a plus q charge, then electric field will be always away from the source charge. So electric field will look like this. At any point, electric field will be always away from the source charge. It will be like this. And when the source charge is negative, then electric field always towards the source charge. Electric field will be always towards the source charge. What is source charge? Because see here, this two charge, one charge that is plus q. So because of plus q, we are actually calculating force on small q. So in that case, electric field will be generated because of actually capital Q. So that's why it is called source charge. And to calculate this electric field, what we have did here, we have replaced this small q charge by a unit charge that is +1. So this charge is known as test charge. So this is source charge, this is test charge. And the coordinate of this source charge is called source coordinate, and the coordinate of test charge is called field coordinate. That is where we are actually calculating the electric field. Okay. So in that case, let's say we have a plus q charge here, and if we want to write electric field at any point r from this charge, and if we have the same amount of charge but now it is minus q, and for this charge if we want to calculate electric field at this point, how we can write this electric field? So in the first case, if we write this electric field, E is equals to 1 by 4 pi epsilon naught q divided by r square into r cap. R square into r cap. So in second case, when the source charge is negative, still the magnitude will remain same. If both the cases the magnitude of charge is same, then electric field, magnitude of electric field will also remain same, q divided by r square. But now since this charge is positive, so electric field will be actually minus r cap direction. If this is the r cap direction, then this will be minus r cap direction towards the center. Okay. So now we know how to write a electric field due to a point charge. Either it could be a positive source charge or it could be a negative source charge. But if it is positive charge, then we want to write the electric field at a distance r. Then how we can write? We can write 1 by 4 pi epsilon naught q divided by r square. If it is positive charge, then electric field will be away from the source. If it is negative charge, then electric field will be towards the source. Okay. But in case if we have a system in which you have more than two charges, more than 1 point charges, let's say 3 charges or 4 charges or 5 charges, And there, if we want to calculate a net electric field at any arbitrary point, then how we can calculate this electric field? So again, let me draw a figure. This is x-axis, this is y-axis, and this is z-axis. Now let's say we have q1, q2, up to qn, n number of point charge, and we want to calculate electric field at this point P. Some arbitrary point P. How we can write this electric field at point P? So what we have learned so far, we can calculate electric field at point P because of only Q1, only Q2, only Q3, or only up to Qn. That is individual charge. But since all the charge actually present here simultaneously, so what we can write, the net electric field at point P will be the vector sum of this electric field. And this principle is actually known as superposition principle of electric field. Superposition principle of electric field. Superposition principle of electric field. According to this superposition, when we will use this superposition principle? When we have more than one charges. If I have a more than one discrete point charge, then for that type, for this two charge or more than, n number of charge we will have, and if we want to calculate electric field because of this charge distribution, then we have to use superposition principle. And if we want to use superposition principle, what we have to do? First, we have to calculate electric field at point P because of individual charge. Let's say Q1, and let's say the electric field at point P because of Q1 is E1, and in this direction. Because of Q2, let's say E2, and it is along this direction. And Qn is along En. Let's say En, and it is along this direction. So then according to superposition principle, what we can do, we can write the net electric field at point P is E net is equals to the electric field at point P due to individual charge, that is E1, E2, E3 plus up to En. Okay. So first we have to calculate electric field at point P due to individual charge, and then if we take the vector sum of this all electric field, that will actually give us the net electric field at point P. Electric field at point P. This principle is known as superposition principle. So again, let me solve an example based on the superposition principle. So for that, just take a look on the second example, example 2. So what is written in example 2? A charge distribution has the charge density given by this. Okay. So this charge distribution, this is some kind of charge distribution, linear charge distribution. And now what has been asked, for this charge distribution, the electric field at point to x naught 0 0 is. Okay. So we have some charge distribution, linear charge distribution, and because of that we have to calculate what will be the electric field at point x naught. Okay. So before calculate the electric field, just take a look on the charge distribution here. Lambda is equals to q into delta x minus x naught minus delta x plus x naught. That is the charge distribution. Let me just rewrite these charge distributions in a different way. Let's say q into delta x minus x naught, and then plus into minus q delta x plus x naught. Okay. So I think 2-3 days ago we have discussed this thing. We can, using Dirac delta function, we can represent a point charge as a linear charge. So compare this concept, what we can say here. So this charge, actually this charge distributions represent a point charge q situated at x equals to x naught. And what about second term? Second term suggests that there is another point charge q equals to minus q at x equals to minus x naught. X equals to minus x naught. So if I want to represent this charge distribution on the xy plane, or let's say on the x-axis, so let's say this is x equals to 0, and then at this point and at this point there is x equals to plus x naught and x equals to minus x naught. So at this point we have 2 point charges actually. At x equals to plus x naught we have a plus q charge, and x equals to minus x naught we have a minus q charge. We have a minus q charge. Okay. So now actually, so this charge distributions actually represent a superposition of 2 point charge q1 q2 at position x equals to x naught and x equals to minus x naught. So now because of these 2 charges, what we have to do, we have to calculate electric field switch point on the x-axis at a distance 2x naught from the origin. So let's say at this point. So this point value x equals to 2x naught. At this point, value of x is 2x naught. So I have to calculate electric field at this point. Let's write this point is P. And also let's write this charge at x equals to x1. It's a q1 charge. So q1 is equals to q. And at position minus x equals to minus naught, we have a q2 charge, and q2 is equals to minus q. Okay. So now according to superposition principle, since we have more than one charge in our system, so if we want to calculate electric field at any point, then what you have to do, you have to use superposition principle. And according to that, what we have to do, first we have to calculate electric field at point P due to only q1. So the electric field at point P due to q1 is E1. What will be the value of E1? It's a point charge. If we want to calculate electric field at this point, what we have to do? First we have to calculate what is the distance of the point from this point charge. So in this case it will be x naught. And we know the value of charge is q. So what will be the magnitude of electric field? Point P, because of q1, it will be 1 by 4 pi epsilon naught q divided by x naught square. X naught square. And what will be the directions? So for directions, let's see, this is the source charge. Now the source charge, in this case it is positive, so electric field will be always away from the source. So in that case, you can see here at this point, away from the source will be along this direction. And what will be this direction? This will be positive x direction. So we can write x cap. X cap. So this is the electric field at point P because of Q1. Similarly, we can also write the electric field at point P due to Q2 is E2. What will be this value of E2 now? So again, for that, first we have to calculate the distance of the point from this charge. So in that case, this distance. What will be this distance? This distance, you can see this is x naught, x equals to 0. So this x equals to minus x naught, and we have to calculate electric field at x equals to 2x naught. So this distance will be actually 3x naught. 3x naught. So then what will be the electric field? What will be 1 by 4 pi epsilon naught. Charge is q. First I am writing this magnitude of q2, that is q, divided by 3x naught whole square. Now we have to write direction. Now since this is negative charge, if it is positive charge, then what will be the electric field at this point? X equals to x naught. It will be away from the source charge, so it will be towards right. But it is negative charge actually, so electric field actually it will be towards the source charge at this point. So towards the source charge mean along this direction. Along this direction. What will be this direction? This will be minus x cap direction. Okay, minus x cap direction. So if you simplify this, what we'll get? We'll get 1 by 4 pi epsilon naught q square divided by 9 x naught square into minus x cap. So this will be the electric field at point P due to individual charge. Now if we want to calculate the net electric field, at point P, what will be that net electric field? Is E net. So according to superposition principle, what we have to do, if we want to calculate net electric field, then we have to take vector sum of E1 and E2. So you know the value of E1, we know the value of E2. Then you put it here and simplify this thing. What you'll get a 1 by 4 pi epsilon naught will be common, and then q square by x naught will also be common, and then it will be 1 and 1 by minus 1 by 9. So it will be 8 by 9, and then 2, if we cancel out, then it will be 2 q divided by 9 pi epsilon naught x naught square into x cap. Okay, So in this way, if we have a more than one charges, and if we want to calculate electric field, so what we have to do, first we have to write electric field because of individual charges, and then we have to take the vector sum of all this electric field, and that will give you the net electric field. Okay. So now we got the idea how to calculate electric field if we have a single point charge, and if we have a more than single point charge, 2 charge, 3 charge, 5 charge, or n number of point charge. So now if we want to calculate electric field due to continuous charge instead of discrete point charge, if we have a continuous charge, then how we can calculate electric field? So for that, let's first write here electric field due to the continuous charge. Electric field due to the continuous charge distribution. Okay, electric field due to continuous charge distribution. So you have already learned how to calculate electric field due to discrete point charge, single charge or more than single charge. Now we want to learn how we can calculate electric field due to continuous charge. So when we talk about continuous charge, either it could be a linear charge distribution, that charge will be distributed over the length, or charge will be distributed over the surface, or charge will be distributed over the volume. The volume. So first we'll learn the standard definitions, how we can write electric field due to linear charge, surface charge, and volume charge, and then using these definitions we'll solve some problem. We'll see how, using this definition, how we can calculate electric field for certain situation, like say electric field on the axis of a charge carrying circular loop, or electric field at the center of a charge carrying arc, or electric field at a distance, at a perpendicular distance r from a charge carrying thin rod. This type of problem we'll solve. So before that, just write the definition here. So first write here, for linear charge distribution. For linear charge distribution. So for that, let me just draw a arbitrary some length, and over this length, let's say some charge is distributed, and charge per unit length, let's say lambda. Charge per unit length is lambda. If we want to calculate electric field at this point P, so now the question is how we can calculate this electric field at point P. So far we did not learn how to calculate electric field at this point P due to continuous charge. What we have learned only electric field. We can calculate electric field due to a point charge, either it's a single point charge or more than single point charge, 2, 3 point charge. Then we can also, using superposition principle, we can calculate electric field. But if we have a continuous charge, we don't know. So what we can do then, we know the concept of elementary length. So what we can do, we can divide this large length into small length like this. So if we break down this large length into a small length, but the small length means elementary length, and consider one such elementary length. Let's say this is one elementary length. and this length of this portion is dl. So our dl is very, very small. So the charge on the elementary length will be lambda into dl. Now this is, since this dl is very, very small length, so charge on this elementary length will also be very small amount of charge, and this tiny amount of charge will behave like actually a point charge. Point charge. And then if we know the distance of the point P from this elementary length, and let's say in this case this is r and this is the directions of r cap, then we can write the electric field at this point because of this elementary length. Or we can write, because the charge on this elementary length will be applied as a point charge. Now we know the distance of the point from this point charge, the distance is r. So what will be the definitions of electric field due to a point charge? It will be 1 by 4 pi epsilon q divided by r square into r cap. So let me write first there. So the electric field at point P due to this elementary length, can write 1 by 4 pi epsilon naught. So it will be like point charge. So what will be this value of this point charge? It will be lambda into dl, and then the distance of the point from this elementary charge is r square, and directions is along r cap. That will be the electric field because of this elementary length. And then if we want to calculate the whole length up from here to here, then what we have to do, we have to calculate electric field due to individual elementary length. And then according to superposition principle, we can take the summation of vector summation of all this electric field. But since in this case charge is uniformly charge is continuously distributed over this length, so we can replace this summation by actually integration. So in that case we have to take an integration if we want to calculate the net electric field at point P because of this whole length, complete charge distribution set to here. For that, what we have to do, we have to take the line integral over this length. Line integral over this length. Okay. So using these definitions, we can calculate a linear electric field because of linear continuous charge distribution. For that, what we have to do, first we have to consider elementary length over the length where the charge is distributed, and then you have to find out the distance of the point from this elementary length, that is the value of r. So once you know this dl, once you know this r, lambda will be given in the question, so you have to put the value of all together, and then if you integrate over the length, that will give you the net electric field at point P. Okay. Same way, if we want to write electric field due to surface charge distribution, so right here for surface charge distribution, for surface charge distribution, so again for that, let me just draw a arbitrary surface here. And let's say some amount of charge is distributed over this surface. Over this surface. So charge per unit area, let's say sigma. Charge per unit area, sigma. So now again, if we want to calculate electric field at this point P, because of this charge distribution, surface charge distribution, how we can calculate the electric field at point P. So for that, what we have to do in that case, we can think it this way. We can divide this large area into small area. We can divide this large area into small area like this. And then consider one such elementary area. and let's say area of this elementary part is ds. So charge on the elementary area will be sigma into ds. Now if this ds is very small, because this elementary area, so ds area will be very small. So if this area is very small, then charge on the elementary area, that is sigma into ds, that will also be very small. So again, this sigma into ds, this amount of charge will be applied as a point charge. So if we want to calculate electric field because of this elementary charge on the elementary area, for that what we have to do, first we have to calculate the distance of the point. Let's say distance of the point P is r from this elementary area. Then we can write the electric field because of this elementary charge. And what will be that electric field? That electric field will be 1 by 4 pi epsilon naught sigma into ds, that is the point charge, divided by r square into r cap. Let's say r cap in along this direction. Okay. So now if we want to calculate electric field at point P due to whole area, then what we have to do? Then we have to consider another elementary area. For that also we calculate electric field here, and then we consider another elementary area. For that we will calculate electric field at point P, and then we'll take the vector sum of all this electric field. But since this charge again on the surface is continuously distributed, so in this case if we want to calculate net electric field at point P, so we can replace this vector summation by integration. So we have to do integration here. Over the which area will integrate? Where the charge is actually distributed. So this whole area we have to integrate because our charge is distributed over this whole area. Okay. So if we have a surface charge distribution, continuous surface charge distribution, and if we want to calculate electric field at any arbitrary point P, then what we have to do? First step, we have to consider elementary area. Second step, we have to calculate the distance of the point P from the elementary area. Then we have to put the value of ds and r in this equation, and we'll integrate this integration over the region where its charge is distributed. If we do that, then we'll get the net electric field at point P because of whole surface. Because of whole surface. Same way, if we want to calculate electric field due to volume charge distribution, so right here for volume charge distribution, So for volume charge distribution, let me just draw some elementary volume, some arbitrary volume. Let's say this is some arbitrary volume, and over this volume we have some charge distribution. And charge per unit area in this volume, let's say rho. Rho. Now if we want to calculate electric field at point P, how we can write this electric field? So just like element length, linear charge distribution, surface charge distribution, first what we have to do here, we have to break down this whole volume into a small volume, into large number of small volume, and consider one such small volume here. Let's say this is dv. And then what we have to do, we have to calculate the distance of the point from this elementary volume. Let's say distance is r, and this direction is the direction of r cap. So then again, the charge on this elementary volume means it's very small volume, and then charge on the elementary volume will be rho into dv. So this amount of charge, again, it will be applied as a point charge. So if we want to calculate electric field at point P, then what we can do, first we'll write the definition of this point charge. So we'll write 1 by 4 pi epsilon naught rho into dv, that is the point charge, divided by square of the distance of the point P from this elementary volume, and directions is along r cap direction. So now if we want to calculate the whole volume because of this complete volume, then what we have to do, we have to consider another elementary volume, and then we'll calculate electric field at point P, and then we'll consider another elementary volume, again we'll calculate electric field at point P, and then we have to take vector sum all this electric field. But again, since this charge is continuously distributed over the volume, so in that case what we can do, we can replace this summation by volume integral. So over this volume, complete volume where the charge is distributed. So in this case, over this volume, we do this volume integration, then we'll get net electric field point P. Net electric field at point P. Okay. So this will be the net electric field at point P because of volume charge distribution. Okay. So these are three standard definitions. Using these definitions, we can calculate electric field at point P because of linear charge, because of surface charge, and because of volume charge. So in next class, we will solve some example using this definition. Okay. So thank you for watching. We'll see you in the next video.